Hi class, this is Professor Dave, and here's a video on the probability of at least problems. And we'll look at the idea of at least one, history of probability, where this started the probability, so that's pretty cool. At least 1 6 in 4 rolls of a die, at least 1 double 6 in 24 rolls of a die, and a couple more examples. Okay, so would you take this bet? That I can roll at least 1 6 in 4 rolls of a single die. Would you take that? Well, kind of on a simplistic level, you would say, okay, well, you have 4 chances, and there's 1 out of 6, so it'd be about 2/3 chance, or 4 out of 6, and you would say no. Okay, and how about this one? Can I roll at least 1 double 6 in 24 rolls of a pair of dice? Okay, let's look at the sample space, right? Sample space for 2 rolls of a dice. You can have 1 on one and 1 on the other. And there's 6 possibilities for the first die and 6 possibilities for the other. So here's a sample space for a rolling 2 dice. There's one way to get a double 6 out of 6 times 6, or 36 equally likely elements. So again, here you'd say, well, you have 24 rolls out of about 36, about 2/3 chance. I wouldn't take that bet either. But it doesn't quite work that way, and you have some very interesting history here. So Chevalier de Marais, back in the 1600s, won considerable amount of money betting that he could roll at least 1 6 in 4 rolls of a die. People were taking him up on it. And then people stopped taking him up on it because they were losing money and he was winning money. Then he said, how about can I roll at least 1 double 6 in 24 rolls of a pair of dice? People took him up on it. Crazy, they're rolling 24 rolls a long time and keeping careful track of it, and he was losing money and he couldn't figure it out. So he wrote his good friend Blaise Pascal, and he thought about it quite a lot, and without calculators they came up with probability. They developed a whole field of probability. So here's our history. So let's do this problem. Okay, so he won a considerable amount of money betting that he could roll at least 1 6 in 4 rolls of a pair of die. Now, how do you do at least problems? What's at least 1? What's a complement of at least 1? We're going to use a complement rule. So the complement of at least 1 6, what is that? Well, what is at least 1 6? Is 1 6 or 2 6s or 3 6s or 4 6s? So the complement of that would be at least 1. The complement of that is none. The opposite of at least 1, which is 1 or more, is none. Okay, so the probability of at least 1 is 1 minus none. That means 1 minus not a 6, and not a 6 on the second roll, and not a 6 on the third roll, and not a 6 on the fourth roll. And rolling a pair of dice is independent, so you can just use the multiplication rule that you can multiply those. So it's 1 minus the probability of not a 6 raised to the 4th, which is 1 minus 5 6 to the 4th, which is equal to 0.518. Okay. So that's actually pretty close. It's actually pretty close to 50-50, 52% chance of winning, and so he was making money. So then he did this bet. What about this one? Well, same thing. What's the probability of at least 1? 1 minus none, so that's not a so that's going to be not a double 6, and not a double 6, and not a double 6 24 times. So what's the probability of not getting a double 6? Well, 35 over 36 to the 24th, and that's equal to about 49%. So he's losing money here and winning money here, and it's a close 50-50. It's pretty fair. It's about as good as casino games. So there you have it. And the key thing here is learning how to solve problems with at least 1. But that is the history of probability. So that's pretty cool. And at least 1 problems. Let's do a couple more examples. Suppose that 75% of people receive refunds when doing tax returns. Suppose that you select 3 people at random. What's the probability that at least 1 did receive a refund? And then we could ask, what's the probability that at least 1 did not receive a refund? Okay, so probability at least 1 is equal to probability of none. What's the probability that they didn't receive a refund? Well, if 75% did receive a refund, then 25% do not. So So they didn't receive a refund, and didn't receive a refund, and didn't receive a refund, all three of them. So that would be 0.25 cubed, and 1 minus 0.25 cubed is about 98% chance that at least one received a refund, and that seems pretty fair. What's the probability that at least one did not receive a refund? Okay, so that could be one didn't receive a refund, or two people didn't receive a refund, and it could have been the first and the third, or the second and the third, or the first and the second person, or all three did not receive a refund. Okay, so we can say, well, that's equal to 1 minus the probability of none. That means none didn't receive a refund. That means they all received a refund. So all three receiving a refund is 0.75 cubed. Right? It's probability that all three received a refund. 1 minus that would be about a 58% chance out of three people, at least one did not receive a refund. So better than 50. Okay. Last example, perhaps somewhat applicable. Suppose that you had an early job interview that you really wanted, and you wanted to make sure that you woke up in time. So you set 3 alarm clocks, each having about a 90% chance of working, and they are independent of each other. And sometimes I apply that. I'll set 2 alarm clocks if I have an early class or an early exam, or for some reason an early volleyball match. Okay. What is the probability that at least one alarm worked? Well, it would be 1 minus the probability that none of them worked. What's the probability that one doesn't work? Well, the complement of 90%, or 10%. So we have probability of none, so that would be probability of 1 minus 0.1 cubed. So all three didn't work. That's really unlikely. 0.13 cubed is 1,000th. So 1 minus 1,000th is 0.999. So you went from a 90% chance to a 99.9% chance. So most likely, one of the 3 alarms will work. And that's applied probability. I hope that's helpful.